We're going to work on an ALEKS problem that deals with calculating the Ka of a weak acid from pH. In this example, the pH of a 0.83 molar solution of hydrocyanic acid is measured to be 4.64. We're asked to calculate the acid dissociation constant Ka and to make sure that our final answer has the correct number of significant digits. So with any story problem, I like to break this down into my given information. They've given us the concentration of HCN. They've given us the pH. And they're asking for Ka. Now, Ka is an expression that relies on the equilibrium concentrations. We don't have equilibrium concentrations, so we're going to have to set up an ice table to figure out those equilibrium concentrations. Before we do that, let's go ahead and work with our pH. Remember, pH is equal to the negative log of the concentration of H3O+. So if we have pH, we can go ahead and solve for the concentration of H3O+. Remember that this will only equal to the antilog of negative 4.64. And I don't want to round too early, so I want to use more digits than I need. And then keep a mental note of our significant figures. So our pH is written with 2 decimal places. So 2 decimal places in the pH just means 2 significant figures in concentration. So I'm going to underline my second significant digit. I'm going to use that entire number, but I'm not going to round to the very end. The next thing I want to do is set up an ice table. So HCN reacts with water to yield H3O+ and Cn-. I want to make sure that this equation is balanced, and it is. So now I can go ahead and set up my ice. Initial, change, and equilibrium. They've given us the concentration of HCN, but this is only a formal concentration. It doesn't account for any of the equilibrium changes. So in other words, this is going to be considered my initial concentration for HCN. In our Ka expression, we don't include water because it's a liquid, so we don't have to do anything for water. For H3O+, initially we have very little or 0 H3O+ and 0 Cn-. For our change, it's always going to be plus or minus the coefficient times x. So for the reactant side, let's go ahead and stick with minus x. And for the product side, let's go ahead and stick with plus x. Since there's an invisible 1 in front of HCN, our change would be minus x. And there's an invisible 1 for H3O+, so this would be plus x. And an invisible 1 for Cn-, so this would be plus x. For equilibrium, we just add up initial plus change. But I do want to remind myself that we solved for the concentration of H3O+. So we solved for x. I want to go ahead and write that down before I forget it. All right, so we've got all that we need in this ice table. The next thing to do is set up our Ka expression. Remember that Ka equals to the concentration of H3O+ times the concentration of Cn- over the concentration of HCN. I go ahead and plug in my numbers and solve for Ka. My final answer depends on significant figures. So our fewest sig figs was in our concentration for H3O+, which is 2 significant figures. So I'm going to underline my second significant digit, look at the number next to it, and decide to keep 3 as is. So my Ka value is 6.3 times 10 to the negative 10. Let's do another example. In this example, the pH of a 1.4 molar solution of hypobromous acid is measured to be 4.25. We're asked to calculate the acid dissociation constant Ka and to make sure that our final answer is in the correct number of significant figures. As always, I'd like to start off with my given table. We have the concentration of HBRO. We have our pH. and we're asked to solve for Ka. Now Ka is an expression that deals with concentrations at equilibrium, so we have to set up an ice table. But before that, let's go ahead and solve for the concentration of H3O+. We have our pH. So in order to find the concentration of H3O+, all we need to do is the antilog of negative 4.25, and this gives us 5.6234 times 10 to the negative 5 molar. Our pH was given in 2 decimal places, so that means our concentration should have 2 significant figures. So I'm not going to round too early. I just want to keep a mental note by underlining the second significant figure. The next thing I want to do is set up an ice table. Make sure that this equation is balanced, and it is. So initial change equilibrium. Initially, I have 1.4 molar solution of HBr. And initially, I have almost 0 H3O+ and 0 BRO-. For my change, it's plus or minus the coefficient times X. So on the reactant side, I have only 1 HBr, so minus X. And on the product side, I have 1 H3O+, so that's plus X, and plus X for BRO-. Go ahead and add initial plus change for my equilibrium. Remember, we solved for the concentration of H3O+, so I'm going to go ahead and write that down. So I've got all that I need in my ice table. The next thing I want to do is set up my Ka expression. Ka is equal to the concentration of H3O+ times the concentration of BRO- over the concentration of HBRO. So I go ahead and plug in my numbers and solve for Ka. Our final answer depends on significant figures, and for this example, the fewest sig figs was 2 sig figs. So I'm going to go ahead and underline my second significant digit. Take a look at the number next to it. Since it's 5 or more, I'm going to have to give that underlined digit a score. So my final answer for Ka is 2.3 times 10 to the negative 9. Good luck and keep practicing.